Electric wire looks simple, but it's engineered through heat, force, and strict testing.
We're inside a wire factory, following copper from raw rod to finished, certified cable.
Before production starts, safety checks and machine guards protect people around high-speed lines.
Everything begins with a thick copper rod, unspooling with steady tension into the first machine.
Copper is refined to high purity, then cast and rolled into long rod for drawing.
Insulation arrives as polymer pellets, blended with color and additives for heat and flame performance.
In the next 20 minutes, we'll follow each step, drawing, coating, twisting, then testing to prove reliability.
And at the end, the wire must survive pulling forces and high heat without cracking or failing. The conductor metal is usually copper for conductivity and flexibility after drawing. Many factories also use recycled copper, but it must be cleaned and refined to meet standards.
Even before drawing, incoming material is checked for size, cleanliness, and consistency.
Insulation materials vary: PVC for cost, PE for low loss, XLPE for higher temperature performance. Additives control flexibility, UV resistance, and flame behavior, while master batch sets the color.
Reels matter too. Stable drums keep tension smooth and prevent damaging bends.
For multi-core cable, extra layers like fillers, tapes, and shields help shape and protect the bundle. The environment is loud and fast, so PPE and strict procedures are part of the manufacturing system.
Cooling and lubrication fluids are filtered and reused to control friction and keep surfaces clean.
Drawing dies are precision tools. A tiny scratch can create a defect that travels kilometers.
Operators continuously watch speed, tension, and alarms to keep the process within tolerance. Before reduction begins, the rod is guided and straightened so it enters each die perfectly centered.
Lubrication forms a protective film, reducing heat and preventing surface scoring. Each die step reduces diameter, increasing length without cutting, just controlled plastic deformation.
If a section looks wrong, it's cut out immediately to prevent defects from reaching the next stages.
A wire plant is a choreography of motion. Reels turning, capstans pulling, sensors checking every second.
The goal is copper that's both strong and flexible, ready for stranding and insulation. Now we move into drawing, where a thick rod becomes a precise conductor in minutes.
In wire drawing, copper is pulled through a series of dies, each one slightly smaller.
Straightening removes coil memory so the rod enters the dies without sideways stress.
Each die shapes the copper by pressure and friction, so die condition and lubrication are critical.
The lubricant chemistry is chosen to reduce friction, control heat, and protect the surface. Capstans provide the pulling force, keeping tension stable from one reduction to the next.
Heat builds quickly at high speed, so cooling systems keep the copper and tools within safe limits.
Cooling loops recirculate continuously, filtering particles that could scratch the wire.
Inline sensors watch for scratches and diameter drift long before problems become visible.
Guides keep alignment perfect, preventing sideloading that could damage the wire or dies.
Across many stages, the diameter shrinks dramatically, while the copper length grows many times over.
Tension control is everything. Too tight snaps the wire. Too loose creates uneven winding.
Drawing work hardens copper, so inline annealing restores ductility by controlled heating.
After heating, the wire cools rapidly to lock in flexibility without oxidation or warping.
Drying prevents water carryover that could contaminate later processes like insulation, extrusion.
Laser gauges measure diameter continuously, keeping the conductor inside tight tolerances. Even microscopic nicks matter because they can concentrate a stress during bending and pulling. Technicians take samples regularly for offline checks, confirming the sensors match reality.
Manual measurement verifies diameter and roundness, catching issues like ovality early. At take-up, a traversing guide lays wire evenly, preventing tangles and crushing. A stable traverse pattern prevents high spots that could kink the wire during later unwinding.
Uniform winding keeps tension stable later when this wire becomes strands inside a cable.
Capstan grip must be consistent. Uneven grip can create tension spikes and diameter variation.
If a break happens, the line stops, the ends are joined, and the restart is controlled to avoid shocks. Splice points are flagged for traceability, ensuring they're handled correctly downstream. Dies wear over time, so scheduled die changes keep surface finish and dimensions consistent.
A die's geometry is microscopic, but it defines the wire you'll use in the real world.
Once stable, the line ramps up speed, producing kilometers of conductor with steady control. Cooling protects the metal and tools, preventing overheating that could change properties.
Dust and debris are captured and removed to protect both quality and worker safety. When a batch is complete, spools move to stranding, where flexibility and handling improve.
Now the factory turns many small wires into a single stranded conductor.
Stranding starts with many thin wires paying off together, each controlled by its own brake.
Balanced tension prevents one strand from taking too much load and distorting the bundle.
Inside the strander, rotation twists strands together, creating strength and flexibility at once.
The twist pattern, called lay, affects diameter, flexibility, and how the conductor behaved under motion.
Changing lay length changes the helix angle, tuned to the cable's final application. Some conductors are compacted to reduce air gaps and create a tighter, rounder shape.
Cross-sections confer the strand count, packing, and symmetry before insulation is added.
The stranded conductor is rewound for extrusion, where insulation will be applied at high precision. Next, the copper core receives insulation, the protective layer that prevents shorts and shocks.
Small adjustments keep payoffs synchronized, preventing jerks that can nick strands or change conductor shape.
Straightening after stranding reduces twist memory, improving extrusion stability in the next stage.
For some designs, rigid stranders build concentric layers for a perfectly round, predictable conductor.
Take-up tension is tuned so the finished bundle stays tight without stretching copper beyond limits.
When stranding is approved, the conductor is ready for insulation extrusion, the next major transformation. Extrusion coats the conductor with molten polymer, then cools it into a durable electrical barrier. Pellets feed continuously so the polymer melt remains stable, without bubbles or starvation.
The barrel heats in zones, melting polymer gradually to prevent scorching and maintain consistent viscosity.
Melt filtration removes tiny contaminants that could become weak spots or pinholes in insulation.
Pressure and temperature must stay steady because they control flow and final insulation thickness.
Before coating wire, the extruder can purge old material to avoid contamination and color streaks. The conductor must be centered precisely so insulation forms evenly all the way around.
Inside the die, polymer wraps the moving conductor in a uniform tube. This is the critical geometry.
Right after the die, insulation is still soft, so the line stabilizes speed to avoid stretching the coat. Cooling troughs solidify the insulation quickly, locking in diameter and surface finish.
Uniform cooling prevents warping and helps keep the insulation concentric and smooth.
Cooling water is controlled because inconsistent cooling can distort diameter and create internal stress.
After cooling, air knives remove water so the next test stations stay dry and accurate.
Laser gauges measure outer diameter and eccentricity, keeping insulation thickness within spec.
If eccentricity rises, the die is centered while running, correcting thickness without stopping production.
A spark test uses high voltage to detect pinholes or thin spots in insulation instantly. Calibration ensures the tester catches true defects without false alarms at full production speed. If a fault is detected, that section is cut out and traced back to the moment it happened.
Many lines print information and length marks, but we avoid readable text to keep the visuals clean. Drying ensures printed marks don't smear during winding and handling. Take-up winding must be gentle enough to avoid flattening warm insulation, especially at high speed. Precise traverse prevents pressure points that can imprint into insulation during storage. Surface inspection catches gels or scorch marks that signal polymer damage or contamination.
Color is tuned by master batch dosing, and transitions are managed to avoid mixed color scrap. Scrap isn't wasted. Many plants granulate and reuse material where standards allow. Changeovers are practiced routines, keeping tension stable so insulation stays uniform.
Thickness checks confirm what the laser sees, ensuring the insulation truly meets design targets.
Cross-sections reveal concentricity and bonding, critical for long-term electrical safety. In larger plants, several lines run at once, each tuned for a specific wire size and compound.
Even small rhythm changes can signal feed issues, so operators correct before defects appear. After cooling, the capstan sets stable line speed and isolates tension from the take-up reel.
Finished insulated wire can ship as a single-core product or become part of a multi-core cable. To build a cable, several insulated conductors are twisted together into one stable assembly.
Cabling forms geometry, keeping cores evenly spaced while fillers maintain a round outer shape. Binding tape holds the assembly tight so it won't open up when the outer jacket is applied.
An outer sheath adds abrasion resistance and protection from moisture and handling damage. Just like insulation, the jacket is cooled carefully to prevent dents and preserve smoothness.
A clean jacket surface is more than cosmetic. It reduces crack initiation and improves durability.
The finished cable is wound onto large drums designed to protect the jacket during transport.
But before it ships, the cable must prove itself in mechanical and thermal testing.
Lay length is controlled here too, ensuring the cable bends evenly without stressing one core more than others.
Wrinkle-free tape prevents pressure points that could imprint through the jacket over time.
Some cables add shielding to reduce interference, using foil and a drain wire beneath the jacket.
The sizing controls the jacket roundness, preventing flat spots as the cable cools and shrinks. Keeping the cable centered prevents scuffs and ensures cooling is even around the full circumference. Many factories spark test the finished jacket too, catching damage before the drum is approved.
Drums are protected so the outer jacket doesn't rub against flanges during vibration in shipping. Jacket quality depends on stable melt pressure. Too low creates voids, too high risks scorch.
Final diameter gauges confirm the overall size, keeping the cable compatible with connectors and conduit. Production isn't finished until testing proves the cable can survive real-world stress.
Samples are taken by batch, tied back to material lots and machine settings for traceability.
Electrical checks confirm the conductor's resistance stays within limits for efficient power delivery.
Insulation resistance tests reveal leakage paths that could grow into failures in humid conditions. Dimensional tests verify insulation and jacket thickness, ensuring enough protection without wasted material.
For tensile testing, the conductor is clamped and pulled at a controlled rate until failure.
The machine measures tensile strength and elongation, how much force it takes to break, and how far it stretches.
A clean, predictable break suggests proper annealing. Brittle fracture can signal processing problems.
Elongation shows ductility. Too low means brittle copper. Too high can mean over-annealed softness. Insulation is tested too, because polymer that turns brittle can crack after years of heat exposure.
Strip behavior matters. Insulation must hold firmly, yet remove cleanly during termination.
Heat aging exposes insulation to high temperatures for set periods, simulating long-term service. Stable oven temperature matters. Small swings can change how polymers age and embrittle.
After aging, the real question is hidden. Has flexibility dropped? And has strength degraded?
Bending after heat can reveal micro cracks that aren't visible until the insulation is stressed.
Aged cracking indicates the compound or extrusion conditions were wrong, and that batch can't ship.
Heat shock tests how insulation handles sudden temperature changes without splitting or deforming.
For higher temperature compounds, hot deformation checks confirm the polymer won't creep under heat.
Cold bend checks winter performance, when polymers stiffen and small flaws can turn into cracks.
Abrasion testing estimates how jackets survive scraping during pulling through conduit and tight spaces.
Some tests look for deformation under pressure, important for cables squeezed in tight bundles.
Flame behavior matter in buildings, so compounds are chosen to resist spread and self-extinguish.
High voltage withstand tests confirm the insulation can resist breakdown at its rated voltage.
Spark testing after jacketing catches any damage introduced during cabling and handling.
If anything fails, the product is isolated and investigated, protecting downstream customers. Investigations trace defects to specific causes: die centering, contamination, overheating, or tension spikes.
Process data helps prevent repeats, turning testing results into tighter control on the production floor.
Every batch creates a record, materials, settings, inspections, and test outcomes tied together.
Retention samples are stored so issues can be traced later, even months after shipment.
Only after passing tests
does a drum enter finished goods, ready for labeling and shipment.
Ends are protected and secured to prevent kinks, moisture entry, or jacket scuffs during transport.
With testing complete, the final step is packaging. Precision length, clean wrap, and safe loading. Before shipping, the factory confirms length precisely, so customers receive exactly what they ordered. Smaller wires are coiled and tied carefully to avoid sharp bends that could stress the insulation.
Protective wrapping keeps dirt and moisture away and prevents coils from springing loose in transit.
Labels carry ratings, batch identity, and standards, important, but we keep text unreadable on camera.
Palletizing prevents movement and crush damage, especially for heavy drums and stacked coils.
Careful handling matters because a dropped drum can dent layers and create hidden insulation damage. From here, finished wire leaves the factory and enters construction sites, vehicles, and machines.
In the field, flexibility and insulation toughness decide how easy installation is and how safe it remains.
In homes, insulation prevents shorts and shocks, while copper carries power with minimal loss.
Outdoors, jackets face weather, vibration, and temperature swings, so material choice and testing matter.
In industry, cables endure heat and motion, so a small defect can become a costly failure. Final inspection is visual too, checking wraps, ends, and jacket surfaces before the truck doors close. From rod to cable, every meter is controlled, inspected, and tested, so electricity stays reliable and safe.